Okay, to go back to the chairman position, we now go to the next paper, number 497, structural reliability analysis of corroded pipeline made in X60 steel based on M5 Model 3 algorithm and Monte Carlo simulation.
Hello, good afternoon everyone. So it's a small substitution because the main author, Mohamed El-Amin and Seger from Algeria, cannot participate. I'm also the last author of this paper, so I try to represent all of authors. The paper is entitled Structural Reality Analysis of Corroded Pipeline Made in X60 Steel Based on M5 Model 3 algorithm and Monte Carlo simulation. This work is a part of quite new idea based on the development of Monte Carlo simulation and Model 3 decisive algorithm. It was a part of cooperation between Algeria, Iran, Portugal, and of course Poland. I represent Wrocław University of Technology, Faculty of Mechanical Engineering, located in Wrocław in Poland. Well, short introduction. I think that it's for everyone clear that in oil and gas pipelines structures we have always the problem with corrosion. Of course, as we can observe, the environment and loading conditions are very strange for material in soils, water, and of course for the aggressive media in oil and gas. So, as we can see from the statistics, the corrosion, internal as well as external, is one of the most frequent causes of failure of the pipelines. Based on this, more than 65% of oil and gas failure were caused by corrosion failure. Of course, in every country, every operating system, we have a problem with this. But the problem is not a corrosion and the protection and many others, but the problem is how to predict the failure, pressure failure, pressure necessary for failure in many corroded parts of the pipe. If we have many kilometers of pipe, for managing staff, maintenance engineers, it's a vital problem how to use it. Of course, we have some solutions for this. In literature, we can base it on the deterministic approach. Of course, I think more close for my head for all engineers to use this approach based on American standards and many others. On the other hand, we have the probabilistic approach. This approach is more close for mathematicians, and of course, if we try to combine both, we can use quite new solutions. Looking inside the probabilistic approach, we can see that we have two ways. One is Monte Carlo simulation, and the second one is analytical method of first order reliability method and second order reliability methods. It's based on the usually solution of the calculation of the failure probability using performance function for n variables. However, all of methods have advantages and disadvantages. Of course, if we try to look inside the deterministic approach, it seems to be more safe approach, but the problem of variation of the statistical scatter of the parameters is still not solved fully in this case. And of course, the probabilistic approach overcomes this, but in this case, if you use Monte Carlo simulation for large amount of defects, you have a problem with the computation time, especially when the probability of failure is relatively low. So we need to develop the methods for better solution with the more robust methods. Of course, on the other side, we have analytical methods. However, in highly nonlinear problem, we have sometimes we receive sometimes the results which are not acceptable with the unpredictable probability of failure. What should we do? Based on the many other disciplines like economy, like hydrology, we can find that M53 decisive algorithm is quite maybe not new, but still developed idea for predictions of the performance function. As an example, if you have simple data collection like this, of course, if you have performance function, the value of this function, if it is above 0, it means that there is no failure. If the value is negative, of course, the failure occurs. Based on two variables, of course, can be burst pressure or size defect. Then you can collect the data, and the key point is, of course, to subdivision of each region for region where we can predict the correct performance function in each subdivided region. Seems to be chaotic structure, but if we subdivide it, we can build the tree. As an example, if you have x2 variable, it could be pressure as an example. If the pressure is less than 4 megapascals, we can develop the further scenarios for predictions. So this idea was used for our case. Monte Carlo simulation is well-known problem which consists in a few steps. So the first step is, of course, clearly based on the randomly sampling the sets of the input parameters according to distributions. Then in the step 2, we repeat the step 1 n times for all samples. And finally, we calculate the probability function of failure after n simulations. Usually it's 1 mile of simulation, so it means that that is very consuming time in the whole defects consideration. If we try to improve such algorithm in subdivision, we use M53 based algorithm. In the first step, we define initial parameters. So, as an example, sample points to calibrate M53 model because there is no extra data, only based on the typical statistical data for calibration. And in the second, in the same step, we try to judge the typical statistical parameters for mean and mu and sigma, and of course distributions. And the next step, we generate the performance function by using M53 model. The step 3, we generate n random samples based on Monte Carlo simulations using previously values. And on 4 steps, we approximate the performance function for n random samples. And the last stage is, of course, to evaluation of the values for the burst pressure of corroded pipe. In our case, of course, we can change the goal of the simulation. It can be not only the pressure, it can be the force, the strength, and all many others. Well, how does it work? We, in our case, try to implement this method for a real structure. The structure was from real object in Poland, from literature. We have the gas pipeline made from X60 grade steel. The length of inspected part is approximately 100 kilometers, and over 1,020 measurement points for each defect. And after simple data ordering and collection, we try to order it in outer diameter of the pipe, the mean value and coefficient of variation, also distribution, and the thickness of pipe, yield stress, ultimate tensile stress, pipe operating pressure. It was 4 scenarios for 5, 8, 10, and 15 megapascals. And of course, depth of the defect, and as well length of the defect at the measuring time. So for each case, the mean value, coefficient of variation, and as well distribution was evaluated. As a result, after the implementing the proposed algorithm in MATLAB simulation, we received, I think, quite reasonable curves for evaluation the allowable pressure for the pipe. As an example, for 4 scenarios, 5, 8, 10, and 12 megapascals, we have reliability index, and on the horizontal axis we have the ratio of the depth or thickness of pipe. In our case, I would like to remind that 0.2 was typically mean value of the ratio D to T. D is 2.45 and T is 12.7. So it means that if we consider, as an example, postulated in the literature reliability index of the level 3, we see that the operating pressure can be on the level approximately 8 will be safe. Of course, if we invert this type of curves, we have the failure probability, and this is completely clear for inversion problem. Well, how about the next parameters? Of course, this is the first attempt of developing existing probabilistic methods, and the next parameter, of course, is the length of the defects. It could be, of course, next question maybe that not only the length, but only the shape, the root radius, many other problems. But if we consider, as an example, length of the defect, we have similar situation with the different ratio L to square of D times thicknesses, non-dimensional reason. And in all cases, if we assume the reliability index of the level 3 and the probability of failure approximately less than 10 raised to -3, it seems that also 8 megapascal will be allowable pressure for this eye. Well, in conclusions, a novel approach based on meta models is proposed to evaluate the failure probability of corroded pipelines. Of course, it needs still development of the data, of the sensitivity of this function, and of course, implementation of other values than only the burst pressure. Of course, we need to consider fracture mechanics parameters, the shape of the type of pipes, many other problems. But it seems that the proposed method of calculation is more efficient than classical Monte Carlo simulation methods. It needs less time-consuming calculation, and of course, we can generate curves based on the defects, probability of failure, and then we can calculate the allowable pressure for the pipe. So, thank you for your attention, and if you have any questions, the session will be possibility to speak about it.
Thank you.